In this video, we're going to spend just a minute to talk about how the scheduler works on a couple of real-world operating systems. The first one I want to talk about is Linux. Linux uses what is called the completely fair scheduler, which I think is kind of a funny name because I don't know what they would have had before. Was it like the completely unfair scheduler or something? I'm not quite sure. So they use CFS. So the idea of CS is really basically something that looks like a multi-level queue, right? So the idea of a multi-level queue is to have maybe different overall classes, right, or categories, right, based on, is this, foreground task, background task. Each of those, right, has some sort of an inherent priority, right? And then within each of those kind of levels, inside of each of those queues, each side of those classes, right, the items in there, right, have their own priorities as well, right? So some things, right, in the same class may have maybe a higher priority, right, than another one, right, and so on and so forth. So you have kind of this overall structure, right, that looks like this, where it's like, well, I have the first class is highest priority, right? This is class 0, this is class 10, whatever, right? And then there's things in here, right, that have varying levels of priority as well. So I have that kind of in a 2D sense. So that's kind of the way Linux is laid out. Now we have a couple of comments in here to talk about. The first is the idea of niceness, and niceness is sort of like it's not a magic number per se, but basically it's kind of a way that you can prioritize a process. So it's like, depending on whether or not you want to kind of be nice to a process or not be nice to a process, right? And I mean that in terms of giving it adequate CPU time, right? You can play with that number, right? So it's basically a way to enforce per process priority. The second thing here, right, is basically this idea of targeted latency. So there is kind of some requirement you can make and basically say, for this particular process, right, I want it to get CPU time every so often, right? We want to basically control the latency there, right? Latency means how long it takes for me to get to something, how long does it take for something to respond. I can basically try to influence that here. Now, one issue is that this isn't something I can really fix, and you can see the question there. The problem is that I can't, in most environments, I really can't have a targeted latency for everything, just because it's like, well, if I have new processes running, right, I don't know, what time it'll take to run them. If I have some sort of fixed environment, right, where maybe I know ahead of time everything is going to be run, well then sure, maybe I can set up a certain latency target and then actually expect to hit it. But unless I know everything in advance, I really can't do that, right? I can't really know for sure I'm going to hit those latencies unless I know exactly all the stuff that needs to run. The last remark here is there's an idea, and we'll talk about this actually more in the next slide, of virtual runtime. So what virtual runtime is somehow representing is like how much time a CPU process has run. The reason why we use virtual there is because there's some scaling that occurs. Right? It's not just the process has been alive for 20 hours. It's not that. It's some sort of a virtual metric to represent how much time our process has spent on the CPU. The idea there is if we can track that, we can make sure everybody kind of is made to take turns. Because what we don't want to be is a situation where it's like one process gets all the CPU time, right? Because maybe it's high priority, and a low priority process never gets a chance to run. Right? That would be an issue. And so the way we kind of address on Linux is with this virtual runtime. So it's basically tracking some sort of a metric, right, that represents how much recent CPU time you've had. I'll talk about that more in a second. Final note there, right, is there's some idea, right, that runnable tasks, right, stored in a balanced BST. Runnable tasks, right, from that you can decide who to run next. That's not too important, but let's talk more about runtime. So let's consider this example. I have two tasks. An IO-bound task and a CPU-bound task. CPU-bound task, right, maybe it has a higher priority. That means it's going to run first. Well, what sometimes happens there, right, because you have a CPU-bound task, while CPU-bound task basically means it's always going to be doing CPU stuff, it'll just sit there, right? It's high priority. It'll always be allowed to go first, so you basically sit there, do that over and over and over again, and your IO-bound process with a little bit different priority doesn't get to run. That's a little bit of an issue. Well, this is actually addressed with the vruntime. So the idea of the vruntime, right, is as the CPU-bound task is running, vruntime will increase. This happens over time, and eventually that vruntime becomes really high for the CPU-bound task. All of a sudden, the IO-bound task, right, will basically be allowed to run because we can see, oh, hey, even though that thing is normally low priority, I can see that it really hasn't been on the CPU that much. So instead, I want basically to give it time. I say the CPU-bound task. So it's basically, right, this vruntime is our metric to record, how much recent CPU time a process has had, right? Over time, basically, vruntime will decay. But right, the idea is that for a higher priority task, right, it'll accumulate that, and then once it accumulates it to a certain extent, then the other processes, right, that have a low vruntime because they have a low priority, those will finally be allowed to run. As a final note here, we kind of mentioned before that in PostX, right, under Linux, right, if I want to, I can specify, basically how I run my threads, right. I can do, my round robin. I can do first in, first out. If you do that, right, what happens is that basically all those things are automatically marked as high priority. They're automatically marked as being, basically they're user land threads, right. They're going user land processes that are going on, right. Those are probably going to be super high priority because the user wants to get a response. They'll end up having, some sort of a priority that's very, very high. So these are kind of the normal processes over here. Right? This diagram is showing you a lot of different priorities, right? So normal processes that are kind of in the background, right, are going to be these over here, right, which are kind of lower ones. These are the ones that have the kind of standard niceness score for how much CPU time we're going to give them. And then the stuff that we do, right, that basically is going to be labeled as real time is typically going to end up over here, right, under this, right? So they'll have a little bit of a higher priority. For our next example, which will be rather brief, we're going to talk about Solaris. And Solaris is a little bit of an older system, but we'll talk about it just to give a little bit of contrast to Linux. So the idea is, again, we have a class-based scheduler, so I have all these different things I can do. So I have time sharing, interactive, real-time system, some sort of this over here, fair share, and these bottom ones basically work a little bit like the proportional sharing we talked about. But we have these different classes, right? These different classes of different processes that could be running, and they kind of imply these different priorities. So each of these classes somehow maps to a certain priority. And I actually have this diagram over here, and this diagram is going from the number basically 0 to 170. Right? If I look from basically from here all the way to here, that's basically 170 is the size of that. These kind of map across, right? So you can see that kind of my TS stuff. Well, my TS stuff maps over here, but my runtime maps to very high priority, right? My system maps below it. My RT maps here, right? My system maps here, right? Fair share maps down here, right? So they all kind of map across. Basically, all those different classes have some sort of fixed priority associated with them. So if something is in that class, it ends up over here, right? So if I have a system thread, it's going to be somewhere in this interval here. Now the idea, right, is I'm basically going to treat this as a kind of a multi-level queue. So what we want to do, right, is basically start at the top, right, process these things here. This is the highest priority, right? The highest priority is there, and then maybe, right, what we can say is that if there's an issue here, and this more applies to kind of this region over here. But if there's an issue, right, maybe something needs a lot of CPU time, doesn't finish, we can basically do the feedback queue thing where we drop it down, right? So maybe a fair share becomes a fixed priority, right? Or a fixed priority becomes a time share, that type of deal. Basically, the idea, right, is that we have that feedback mechanism where I have things that are take up a lot of time, basically get deprioritized and kind of funneled down. So that's already kind of built into there. The comment here, right, or the question here, right, is on the slides is higher priority processes are given smaller time slices. Why? Basically, the idea is there, right, is that, and this is kind of coming out of the blue a little bit, I guess. But the idea, right, is I have a bunch of high priority things. I want to minimize the response time, right? I want to basically go around and say everybody gets a little slice of time, right? So you think about doing a round robin, give 10 milliseconds, whatever it may be. The idea there, right, is that if I have a batch of high priority processes that are running high priority threads, well, they're all high priority. I can't really pick and choose which one of them I want to pick. Who's my favorite? I can't really do that. So instead, I have no choice but to go round and round. Right? I need to go everybody a little bit of time, a little bit about time, a little bit of time. That way, I minimize everybody's waiting time and kind of minimize everybody's response time as well. So final couple of notes. If I have two processes in my system that have the same priority, I'll basically service them, round robin style. And then also, so that's one thing. The other thing to mention here, and it's mainly for the graphic, is that sometimes you do have processes that maybe share the same exact priority number. Because of that, this graphic doesn't really show you like the population of the different classes. So this isn't saying that there are going to be more real-time threads than there are system threads. Even though there's more kind of on the graphic here, just a mental note is because things can have the same priority, that means I could have 10,000 things inside a system, right? It's just that they're all going to have the same priority, and then I have less, right, in real time, right? I only have 60 or something like that. So that graphic doesn't really map to how many things we expect to have in each of those different classes.